Hey, welcome back. We are looking at our states of matter, and I know. You know your states of matter, solids, liquids, gases. But our goal is to think about some of the scientific vocabulary to describe our different states of matters and the properties they start to exhibit, as well as really drill in and think about it at the particle level. And I know we saw this a little bit on our PhET simulation on Friday, but we're really going to try to think about how are these particles moving, interacting to give us what we see. So states of matter, you know them, solids, liquids, gases, here we go. So some things we can start to describe are some of our main properties, and these are on page 40 in your notes, by the way. If at any point you need to stop, pause, rewind, refresh, you know the deal. So our properties, when we look at our different materials, we know we can talk about whether our particles expand or when we put them into a sealed container, whether or not a particle is fluid. And we know what fluid describes. Usually we think liquid, but could be something else. Fluidity is just the ability for one particle to move past another particle. We know liquids are fluid. As we kind of slosh our materials, we know that those particles can move past each other. When we start thinking about our density, a substance could have high or low density, just referring to how closely packed those different particles are. And we can start to think about whether or not it can be compressed, which ties into our density a little bit, but compressibility. Can we squeeze that material and actually make it a smaller space than it was before? We also have diffusion and effusion. Diffusion, you know, hopefully, from Bio 1, when we think about osmosis, diffusion is our ability to move from an area of high concentration to low concentration. This is spontaneous mixing. I think of bacon, right? You're in your room, folks are making bacon, and you're just sitting there like, oh, you can smell the bacon because those particles have continued to mix and go throughout your materials to create a diffuse situation. Not to be confused with effusion. You probably haven't heard this one before, but you know what it is. Effusion, our particles are so small and moving so fast that they can escape. They can escape through little microscopic holes because of the pressure that they're under and the movement that they are undergoing. I think of Bed Bath and Beyond is closed. Bath and Body Works. You know this. You might not know the term, but you know this. If you take your perfume or your cologne and you hold the opening up, you don't spray it, but you hold the opening up to your nose and you smell. The reason you can smell it is because little particles of perfume or cologne are escaping out of that opening. And if left unchecked, it would eventually all escape and you'd run out of the perfume or cologne. The other one, you know, probably is from childhood. You got your little rubber balloon and you're like, I'm going to keep it forever. And you tie it to your bedpost. And then, you know, a week later, it's like, right? It's all deflated. That's because helium, so small, smallest on the periodic table, can escape out of all those little microscopic holes in the latex. And as a result, we lose our buoyancy and our balloon sadly deflates to the floor. So diffusion, mixing from high to low. Effusion is escaping. Similar properties, but technically different terminologies. Take a second, pause the video, draw me what you think a solid would look like at the particle level, what a liquid would look like at a particle level, and a gas at a particle level. Cool. Now you've drawn them. Do be on the lookout for liquids because we know solids, they're going to be close together, fixed, rigid positions, orderly. Liquids are still close, just not as orderly. Had a lot of pictures of liquids and gases that got kind of similar. Gases, they're way spread out far apart in our container, but our liquids should be kind of at the bottom. We know that they get pulled down towards the bottom of our solution as we're thinking about our different types of liquids. Cool. Let's talk about solids then. I'm not going to belabor this. You know your solids. You know that they are of definite shape and volume. They are rigid, locked position. Because of this, because of their attractions, they have a definite melting point. There's a temperature at which it changes phases. We know that it has a high density. Those particles are close together in a small or given amount of space. We know that they're hard to compress. And some things do technically compress more than others. But as a whole, they're pretty incompressible. You cannot get those particles much closer together than they already are. Our liquids have a definite volume, but no definite shape. Because the particles are fluid, they can move past each other. They're going to assume whatever shape the container happens to be. We know that they're fluid. I already talked about that, moving past one another. But because they're still close together, they are more dense than our gases. If you think about playing Marco Polo in the pool, you know it is harder to run through the dense liquid water than it would be if you're playing tag in the gym, for example. And we've got our incompressibility of liquids. We use this for hydraulics. If you think about like a mosh pit, right? I can get in a mosh pit and I can bounce my way to the other side. If I took a board and I pushed on one side of the mosh pit, everybody would just bump into each other and the people on the far side would fall over. This is how we use our hydraulics and our different excavators and tractors and tools for our heavy equipment. They do have a surface tension because they are still attracted to one another. We still have a surface tension. If you've ever done a belly flop in a pool, you know that this is true for our liquids. There's still some attraction going on there. Then we get to gases, and these are the easiest to kind of observe or to monitor or measure. We know that they expand. They're going to fill whatever container you put them into. As a result, they also diffuse from higher areas of concentration to low. Gases are also fluid. Here in a little bit, the bell is going to ring. You're going to gain a bunch of energy and you're going to expand to fill the city of Liberty and North Kansas City as you fill your new container. And you're going to pass other people while you do that. You're going to become gases and you're going to leave to head on out for the day. Because they spread so far out, they have a very low density with lots of empty space. As a result, we can compress them. We can squeeze those gases. Let me get my syringe for you. Just filled my syringe full of air. I'm capping it at the end. As a result, I can compress this syringe because there's empty space between the particles because they have expanded so wide. The question now is, how do we explain those properties? So here's all these things we observe, solids, liquids, and gases. How do we explain it? The way we do that is with the kinetic molecular theory. We sometimes call it KMT, the kinetic molecular theory. Well, what is our kind of essential question today? What is the kinetic molecular theory? And how does it relate to our different states of matter? How can we use it to explain these properties we see for solids, liquids, and gases? And there's kind of 5 assumptions, and we base them kind of on gases just because they're easiest to see and easiest to measure when we're looking at our different substances. But real quick, what does kinetic mean? Well, there's 2 types of energy. There's kinetic energy and potential energy. Think about your roller coaster. When you're at the top of the hill, that is potential or stored energy. Then you go over that peak and away you go. All of that potential gets changed into motion, and that motion is the kinetic energy. And this makes sense. When we describe solids, liquids, and gases, we're saying, how do those particles move? And how do we kind of measure that energy of their motion, how quickly they're moving? And so our KMT is kind of based on 2 ideas. The first idea is that our particles are in continuous rapid random motion. They're always moving. This is true. It's weird to think about, but your chair is moving right now. You can't see it. The scale's too small, but those particles are vibrating in their fixed position. Not unlike our classroom sitting in their fixed, rigid position. You're still vibrating in your chair a little bit. You're taking notes. You're doing your hair, whatever, but you're in a fixed position, orderly, but still moving. Even as a solid, you're still moving. And as a result, this motion has consequences. It's what gives us these properties that we see. Cool. So we need to talk about a real quick definition, ideal versus real. An ideal gas or an ideal date. It's the perfect date, March 24th, not too hot, not too cold. An ideal date is the perfect date. It goes exactly the way you want it to, not to be confused with a real date, which is what actually happens. You get a flat tire and they don't have your reservations and they run your favorite mac and cheese. I don't know. But an ideal gas is perfect. It fits exactly all of these assumptions we're about to talk about. It does exactly what we think it should, based on this theory that we've come up with. Real gases do not. They don't behave exactly the way we want to. The reason there's a distinction basically is because of water. Water is highly polar. As a result, there are attraction between those particles and it starts to do some weird stuff. For us, mathematically, the real gases involve calculus when you start solving problems with real gases. The good news is most gases behave close enough to ideal gases under normal conditions, 1 atmosphere of pressure, room temperature, that we can kind of treat all of our gases as ideal gases. They do what we expect them to do, which is awesome. It makes it way easier when we start looking at the math. Cool. So our assumptions of our kinetic molecular theory. Our first assumption is that our gases are made up of a huge number of particles that are far apart relative to their size. When we think about a sample of a gas, we got teeny tiny particles way far apart as they're moving around in space. And so this explains why we got mostly empty space between our particles, because they're far apart relative to their size. This explains why we have a low density. Big space, small number of particles, low density. And as a result, we can compress them. Because there's open space, we can squeeze those particles closer together. They have high compressibility. Our second assumption of our kinetic molecular theory is that these particles are always moving, and especially in a gas. They are in continuous, rapid, random motion. If you've heard of Brownian motion, this is kind of what we're describing. It is this motion that we measure as thermal energy, as temperature. And we'll talk more about temperature units a little bit later this week. But it is these particles movement that provides our thermal energy, our kinetic energy as measured by temperature. And this explains why gases expand. They're always moving, so they'll just move away from each other as they're randomly moving around until they hit the container wall. It also explains why they diffuse and effuse. They diffuse and effuse because they're always moving, and they'll just find whatever little opening or whatever little hole, or they'll spread out until they mix evenly throughout our sample. Our third assumption is that when we have collisions, which we're going to have, you know that these gases are whipping around, they're going to collide and they're going to create collisions. These collisions are said to be elastic collisions. You think of your rubber band, you stretch it out, release it, it goes back to its original location. There's no transfer of energy, or sorry, there's no loss of energy. That the energy is either kept constant or is maintained throughout our changes. This explains why there's no loss or gain of thermal energy. No loss or gain of thermal energy. Our fourth assumption of our kinetic molecular theory is that there are no forces of attraction or repulsion between our particles of gases. It's not like they're going to come together, hit, and then stick. No, it's like pool balls. They're going to hit and rebound and collide and bounce and collide and bounce. They continually collide and bounce. We measure this as pressure. We'll talk about this more tomorrow. And you know this. If your tire is flat, you put more particles in, they're going to collide more often, which is going to increase the pressure here on planet Earth. And this is why our gases expand. If they hit something, they just bounce off and they keep on trucking. This is also why they act as fluid particles. As they hit and bounce and hit and bounce, they can slide past one another. It's also why they have low density. Sorry, I'm getting ahead of myself. Low density, they spread out again because there's no forces of attraction between them. Our fifth assumption, and there's a little bit of math here, we'll talk about it when I see you again. We actually can measure the kinetic energy. It's measured as temperature. The average thermal energy, the average temperature of our particles, is dependent on the temperature, and it depends on two factors, the mass and the velocity. The bigger the particle, the slower it's going to go. You got to put more energy into it to get it to start to move, or vice versa. I call it the bike versus the bus analogy. Right? If you have to get hit by something, you'd rather get hit by the bike because it's going to have less kinetic energy because it's less massive. But if we wanted them both to collide with the same amount of energy, bus would have to be going way slower. The bike would have to be going way faster in order for those energies to be the same. And so when we think about two gases, or like gases in this room right now at room temperature, the heavier the particle, the slower it is going. As temperature goes up, the thermal energy goes up. Well, the particles can't just suddenly become more massive. And so as the temperature goes up, the velocity goes up. Particles start moving faster. And we see that there's a greater temperature and velocity. So if we're thinking about ice versus water or water vapor, the difference between these is the temperature. As temperature goes up, the particles have more kinetic energy and they start to move faster and faster and faster. Cool. I threw a lot at you. This is how we start to think about how our particles behave. It's what gives us our properties or behaviors for our solids, liquids, and gases. Your homework for tomorrow is going to be to go back through your notes, write down any questions that you might have, and then, or highlight any questions you might have, and then complete your notes summary. Coming back tomorrow, we'll start with that. We've got some demonstrations I didn't get to do via the video, and then we'll start talking about our pressure units as we go into our last day with our seniors. Have a wonderful day. We'll see you tomorrow.